Okay. Well, we'll try this out and see. I guess this is fine. We'll see what we can do. Okay. All right. So we left off. We covered on Thursday the Metropolis algorithm, right? So Metropolis algorithm and the Metropolis Hastings algorithm. It's like it seems to stylize my writing a little bit. So we have the Metropolis algorithm and Metropolis Hastings algorithm. And the idea is, we have a target PDF or target distribution. P of x, and then we wish to get a sample from P of x, but we cannot sample from it directly, right? Okay. So we set up a Markov chain to do the job. And the way this will work is, so with the Metropolis algorithm, what do we have? We have a proposal distribution. Q of x, x prime given xk. So this is this proposes new values x prime based on our current location x sub k. Okay. And then we create or we calculate an acceptance ratio. I don't know what I'll call this, but which is going to be probability of x proposed divided by probability of x current, right? So this is probability of proposed divided by probability of current under the target PDF, okay? And then we accept x prime, the proposed value, with probability equal to the minimum between 1 and the acceptance ratio. All right, and then if we reject, we reuse the current x value. All right, how do I scroll down here? All right, is this okay? So this is math. What is this? Get started with math. Write your equation in ink. Select your equation. Type. Tap the math button. Wow. All right, let's see if this. No, that's that. How do I do this? I don't know how to do this. All right. Okay. I'm very fascinated. Let's try this. Okay. I'm going to say, no, okay, forget it. All right, we'll do that. We'll play around with this later. Okay. All right, is that all right? So this should be familiar. You guys had some exercises. You did the Metropolis algorithm to kind of sample from this broad thing, and we saw that even if you have a terrible starting point, it gets you to kind of the zone of interest. Okay, and then we also saw that there's no need to calculate a normalizing constant, right? Because in the acceptance ratio, because you're using the probability of the proposed divided by the probability of the current, if there is a normalizing constant in there, that normalizing constant cancels out. So there's no need to calculate a normalizing constant. Okay, so all right, because we use, all right, let's see if this does anything. Okay, and then we'll tap math. Kind of. Let's see, fix it. Circle the part of the equation you want to fix, this part. That's a P. Wow, look at that. I want the big P here also. Whoa, all right. Done. Okay. Ink to math. Oh, wait. Okay. I want it bigger though. All right. This is oh gosh. Okay. Oh, I don't know how to use my computer. How do I make this bigger? Okay. Well, all right. We'll stick to the pen. I know how to use that. Okay. Because we use this thing, right? There's no need to calculate a normalizing constant. Okay, so if P of x is equal to C times F of x, right? P of x prime divided by P of x sub k is going to be equal to C times F of x prime divided by C times F of x sub k, which will just be F of x prime over F of x k, and so we're good. So no, C does not need to be found. And that's perfect for us. This is kind of fun, scrolling down instead of new pages. This is perfect for us because in Bayesian statistics, we often get things in the form of where we have a function that's proportional to, right? So recall, in Bayesian statistics, the posterior distribution, okay, the posterior distribution is, the probability distribution of the parameters given the current data, right? That's going to be the probability of your parameters theta given the current data is equal to, this is the likelihood, times the prior distribution divided by the probability of the data, okay? And we said probability of the data is equal to the marginal probability, which is a constant, and difficult to calculate. Okay, and so again, this is effectively a normalizing constant. So, let C equal 1 over P of D. Okay, then you have probability of theta given the data is equal to just C times probability of the data given theta times the probability of theta. Okay, and if we use Metropolis algorithm, we do not need to calculate C or this marginal probability. Okay, and that's perfect because oftentimes generally it's easier for us to get the likelihood and for us to get the prior than it is for us to get this normalizing constant. Okay, so the numerator is not going to integrate to 1, but that's okay. When we use this ratio to calculate our acceptance ratio in the Metropolis algorithm, this problem goes away. Okay, so I'm going to spend the rest of our class time doing just an application of the Metropolis algorithm that I think is pretty cool, okay? And, because, I don't know, maybe you had fun with the homework assignment, maybe not, I don't know. But the distributions I had you sample from are not too exciting because in general we can generate samples from the normal distribution and these existing distributions quite easily. But I'm going to give us a scenario that the distribution is completely unknown to us. Okay, and so credit where credit's due. I've posted some articles on CCLE, by Percy Diaconis and I don't know some other guys talking about using MCMC for the decoding of ciphers. Okay. Decoding of ciphers. Okay, so a cipher, this is where, I don't know, maybe when you were a kid in like 6th grade, when you were 10 years old or 12 years old or something, you had these fantasies of being a spy and you had to write like secret messages to each other, right? And because you didn't want your sister to encounter them or something. and so a simple cipher is you have the alphabet, right? And then okay, and then maybe sometimes these are on like a decoder ring, and so on one side you have these letters, and then on the other side you kind of match them up, and then you just have another set of letters, and it would be like A becomes the letter K, and B becomes the letter G, and C becomes the letter E, and D becomes, I don't know, Z, and A, and X, and P, etc., 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 okay? And it's just every letter corresponds to another letter in the alphabet, right? So each letter gets mapped to a new letter. Okay? And then, and so under, with this cipher, the word I don't know. Yeah, bed will becomes what? G-A-Z, okay? All right, so the word bed becomes GAZ, right? And then to decode, somebody would need this part, and then they would transfer it back and get the original message, right? So decode, we go, from GAZ and get BD, okay? And so you could pass messages to one another, and the person who encounters it will not know what you've written. Okay. And so that's the idea of a cipher, okay? And apparently this came about in prison. People were sending messages to each other, and the guards would intercept them, but they were ciphered, and the guards wanted to know, are the prisoners up to no good? And this is not encryption, right? Encryption is done by the computer, and it's far more complicated, right? But encryption to do by humans is like not possible. But ciphers by humans, this is a rather rudimentary thing, so it's simple to do. Okay, so anyway, the guards intercepted these notes to one another, and they want to figure out what were they saying, but to decode it without the the encoding part is kind of hard to do. So what can we do, right? So there is a quote, a secret mapping that maps the letters of the alphabet to a new set of letters. Okay. And this is, we can think of this, the secret mapping can be thought of as our theta. This is the parameters that we want to try to figure out. Okay, and so the correct theta is one that maps GAZ back to bed, right? It's like the money is hidden under the bed or something, right? And you got to figure out what it is, right? And we can, but there's, there's how many mappings are possible, okay? If we think about, what is the, space, what do we call this? The sample space? What is the space of theta? How many mappings are possible? This would be all possible letter mappings, right? Okay, and so how many are there? 26 factorial, right? This is 26 factorial mappings. A could be mapped to any of the other 26 letters, and then B can be mapped to the remaining 25 letters, all the way down to Z. So there's 26 factorial mappings, which, let's ask, what is that? It's a big number, right? Let's see. What is 26 factorial?
The answer
is, okay, so this says 4.0329 times 10 to the 26. Okay, coincidentally, that's a big number, right? It's not infinity, but it's a very big number, okay? All right. So, what is this? There's 26 factorial mappings, and this is too many for a computer to just brute force, okay? So, I mean, you could do a brute force attack, but it's still too many, right? Still too big for a brute force attack. Okay. A brute force attack being you just start with one mapping and you just change one letter at a time and you go through it, okay? So we need a better way to try to figure this out. And so we're going to use probability, okay? We will use probability to help us evaluate the mappings. Okay, so here's our text. Our text is G, A, Z, right? Okay, so under one mapping, so here's a potential mapping. Has maybe G corresponds to K and A I guess it would be the other way. But you figure out what it could be, and maybe it's like K, N, and Q, right? And maybe these map to GAZ. And then so under this mapping, so if we use this to decode, we get K and Q, okay? And by looking at that, we can say this is probably not the correct, this seems to be an unlikely mapping because it seems unlikely that the word that the prisoners were trying to cipher was K and Q. Maybe that means something, but this is not a real English word. It seems unlikely that this is the correct mapping, right? K and Q is not a real word, so it is unlikely that this mapping is correct. Okay, but another mapping maybe with GAZ gets mapped to I don't know, HIT, okay, HIT, okay, just 3 other letters, right? So this seems a lot more likely. Okay, and obviously we would need more text to try to figure out what is the correct mapping, because there's probably thousands of 3-letter words that would all seem like potentially correct, right? The correct one is bed, but any other mapping that produces a correct word would seem legitimate, right? And so we would have to see, hopefully we have enough text so that you can see how all of the letters in the full text get mapped, and you can evaluate it that way, right? Seems a lot more likely, okay? And we need more text to fully evaluate a mapping, okay? But it's the idea of, is this likely, if the mapping we're using decodes into real words, then it seems like it is correct, right? And other mappings that decode to nonsense words are less likely to be correct, okay? So mappings that produce real words in the ciphered text are more likely, or we'll say will have a higher probability okay, and then mappings that produce nonsense words, nonsense, are less likely. Okay. So part of our strategy will involve, part of our deciphering strategy will involve checking to see if the decoded text has real words. Okay, so we're going to decode the text, okay, run it through the cipher. We're going to say, all right, here's a potential mapping. Let's run our intercepted message through this potential mapping and see what it produces. And if it produces some real words, that's a good sign. If it doesn't produce any real words, then it's a bad sign, right? Or it's a sign that our current mapping is not likely to be correct. Okay, so part of our deciphering strategy will involve checking to see if the decoded text has real words. Okay. That's great if your mapping can produce real words in the first place, right? But there's going to be, with 26 factorial possible mappings, there's going to be a lot of mappings that will still not produce any real words. Okay? And we need a way to still evaluate those because some of those mappings are better than other mappings, right? So we also need a way to evaluate mappings that do not produce real words but are, quote, better than other mappings. Okay, and so, maybe one mapping produces, let's see, this, okay? And then another mapping produces right? And so, both of these, neither of these are real words, okay? At least to my knowledge, okay? Neither are real words. So if we used just the dictionary that says, is this a real word, yes or no, both of these would get scores of, would get the same score, not a real word, right? However, the mapping up top seems a lot more readable than the mapping on the bottom, right? It at least seems like, maybe we're getting somewhere closer to the real mapping, right? The mapping up top, okay? It kind of has some structure to it, right? So the mapping above, the, if we have, we'll say we have two mappings and competing mappings Repeating mappings produce this and this, right? Okay. All right, and the first mapping seems more correct than the second mapping. All right? Because, you know, we're used to seeing T followed by E and E followed by R. Those seem fine. But to see F followed by J and J followed by X, I don't know, I can't think of very many words in the English language that have that kind of sequence of letters, right? So we see many words where T is followed by E and E is followed by R. So this kind of corresponds to, you know, a higher probability. And then on the other hand, I can't think of any words or F is followed by J. I don't know, maybe there's, oh yeah, there is, like fjord, right? FJ, okay. So few words. So we'll just say very few words where, you know, F is followed by J and J is followed by X. Is it okay? So we don't have very many words where F is followed by J or J is followed by X. Okay, and so our other strategy will look at two-letter combinations. And we will give high scores to combinations that are common and low scores to combinations that are rare. Okay? So the other strategy combinations, okay? So we give high scores to letter combos that are common. Like TH or, you know, NG, you know, or, you know, whatever, etc., you know. Common letter combinations, okay? And then low scores to, you know, other letter combinations. Okay? And so we'll use that to kind of help us evaluate one over the other, and we would give a higher score to this mapping and a lower score to the second mapping here based on the two-letter combinations. We'll say, how common is TE? Oh, that's pretty common, high score. How common is ER? That's also pretty common, high score. Things like that, okay? How common is FJ? Pretty rare, low score. How common is JX? Very rare, very low score. How common is XX? Also very rare and stuff like that. You know, so this would get, you know, a much lower score than the other. All right, is that okay? Okay, and so in our, okay, so you have to imagine some, I don't know, abstract probability space. okay? And it's a discrete probability space, okay? Discrete probability space with 26 factorial, I guess, states. Okay, so you have some kind of, I don't know, discrete. This is just some abstract. Okay, we're imagining in the abstract, right? And then you've got 26 factorial locations here, and if I were able to put some kind of grid over this, okay, most of the locations have probabilities close to 0. Okay, because the question is, what is the probability of this mapping given this is the data that we've intercepted, right? This is given that this is the message we intercepted. What's the probability that the letter mapping they used was this, right? Okay, because it's what is the probability of this mapping, of a particular mapping given that the intercepted message is D, right? So you got the data, your D. What's the probability that this is the particular mapping that they are using? So most of these is flat, okay? But maybe in a few pockets there's going to be like this is the correct mapping, and it's going to have a high probability, okay? And then maybe there's some other mappings that are not correct, but they have higher better probabilities and stuff, okay? Because one produces words like hat and hit and I don't know, and then the other one produces the correct mappings bed along with other stuff, and who knows, right? And so here's the beauty of the Metropolis algorithm is that, again, we can start in a terrible location because we have no idea what mapping to use in the first place. We start in a terrible location, we propose a new mapping, and eventually, maybe we'll eventually get to the zone that is kind of correct, okay? With the Metropolis algorithm, we start with an arbitrary and likely terrible mapping, okay? And then, we propose new mappings and generally move towards favorable mappings. Right? Because according to the Metropolis algorithm, if something has a higher probability than your current probability, you are definitely moving there. And if something else has a worse probability, you might move there, okay? It's not that you never move in the wrong direction, it's just you are less likely to move in the wrong direction. And you will, if you evaluate something and its higher probability, you always move in that direction, right? Because the probability of moving is the proposed versus the current. And if the proposed has a higher probability, that probability is over 1. You go with probability 1. Okay, so we move towards favorable mappings. And so if we let our algorithm run long enough, eventually what we end up sampling will be mappings that are either the correct mapping or something similar to the correct mapping, right? So if we let our algorithm run long enough, our samples drawn will be, the correct mapping along with other mappings with high probability. Because the goal of the algorithm is to get a sample from our target distribution, which gives higher scores to the correct and likely mappings. Right? Does this kind of make sense? Okay, let's again take a look at kind of from a Bayesian perspective. So we've got the probability of a mapping given the data, okay? Probability of a particular mapping given the data is going to be equal to the probability of the data given a mapping. So this is the likelihood of the data given a mapping multiplied by the prior distribution over all mappings divided by the marginal probability of the message D. Okay? And this is a constant. Okay. So again, we talked about how we can ignore this probability D, this marginal probability, with the Metropolis algorithm, okay? We can ignore P of D with Metropolis algorithm. Okay, and then probability theta, this is our prior distribution over the mappings. Okay, and so this reflects what we believe about the mappings, saying, I think this mapping is more likely than this mapping, or something like that, before even looking at the data. Okay, so this is, our beliefs about the mappings. Before looking at the data. Now, before we look at the data, we really have no clue which mapping is going to be correct, right? So all 26 factorial, before looking at the data, all 26 factorial mappings are equally likely in our mind, okay? So before looking at the data, all 26 factorial mappings are equally likely. So probability of theta is also a constant. Okay, it's technically 1 over 26 factorial because every single one is equally likely. So if all possible mappings are equally likely, each mapping has a probability of 1 over 26 factorial. Okay. So this is going to be the prior distribution of theta. So this boils down to, so our posterior distribution, the probability of the mapping given our data is just proportional to the probability of the data given the mapping. Okay? So we just need a way to figure out the likelihood of the data given the mapping. Okay? We just need to find this, and then we can sample. We can, try to sample. Probability of theta given the data. All right, is this okay? So the probability of the data given a mapping theta. Okay. Are there any questions on this? I'm like really excited. I don't know if you guys are excited to see this work in action, but in my mind, it's like, we've been spending all of this time going through stuff, and here's something that's actually kind of cool, but I got to explain the math behind it, right? Okay, so we're going to break down the probability of data given theta. This is going to be, we're going to have the probability of kind of basically, so the way it's going to work, so to get this is we will run our message D through the potential cipher, okay, and get a quote decoded message. Okay, and I put decoded in quotes. Maybe decoded is not not the right word, because this could still be garbage, right? Here's a potential cipher mapping of letters. We run it through and we say, okay, let's evaluate this decoded message, okay? And get a decoded message, and then we evaluate the likelihood of this. The likelihood of the quote decoded message, which will consist of the probability of kind of your 2-letter transitions, 2-letter combos, times the probability of, real words versus, times the probability of the real words, right? And so, if you're encoding a message or decoding a message, and the decoded message produces the word the, often, then you're like, oh, this seems pretty good, right? And if it, and so, the has a very high probability, is has a high probability, and stuff like that. Other words, instead of it producing is, it produces ox. You'd be like, ox is a real word, but it seems weird that we're talking about oxes in the message, okay? So we're gonna do this, okay? And so the 2-letter combos, we're going to, so let's talk about the probability of the 2-letter combos. Okay. So first of all, we need to figure out step one is what letter combos are common in English? Okay. Now we know like TH is common and certain things, and other letters like the ones that involve the letter J are going to be uncommon because J is just not that popular for a letter, right? You know, JA or something. So what we'll do is we will read, you know, a bunch of text, and in this case we use War and Peace. War and Peace is we'll use an English translation of War and Peace, I should say. Okay, so War and Peace is a Russian novel, and it's super long. I don't know what it's about. It's about war and peace and some philosophical musings. And well, anyway, we'll read that in, and then we'll just have the computer evaluate and just tally up every single combo, right? So there's we're going to have a 27 by 27 matrix, okay, 26 letters and space, okay, and then the computer will tally up you know how often it sees each combo. So it's going to say, how often do I see A followed by A? How often do I see A followed by B? And it's just going to go through and it's going to count them all up. We'll add all of those up. We divide by the total so that the whole thing adds up to 1. Okay? And then so we get a 27 by 27 matrix that adds to 1. So we'll have the computer will tally off in how much it sees each combo, and then divide by the total. Okay, is that all right? So we'll do that. So now we have an evaluation of which letter combos are most common. And then step 2 is we find the probability of our quote decoded text. Okay, and so normally this would be, if the decoded text is, I don't know, JAZZYF PUN, okay, something like this, it would be the probability of JA times the probability of AZ times the probability of Z space times the probability of space Z times the probability of ZY, etc., etc., etc. Okay, so we're going to look at each 2-letter combination in our thing and do this. Okay, this will lead to very small probabilities, to tiny number, and the computer, because of its floating point arithmetic, this will run into problems. It's not going to be able to represent this tiny number. Okay, so instead leads to tiny numbers, problems with floating point. So what's a workaround that we can use? Instead of dealing with tiny decimals, what can we do? We can convert them into logs. Okay, we'll take the logarithm of all of these numbers. So instead of getting numbers between 0 and 1 in probabilities, we'll get just negative numbers between negative infinity and 0, and then we can add them together. And the computer's a lot better at adding negative numbers than it is at multiplying really, really, really tiny numbers. Okay, so instead, we will take the log and add them. So we'll get the log probability will equal log of the probability of JA plus the log of the probability of AZ plus dot, dot, dot. Okay, and so this will lead to a negative number. Okay, is that all right? Oh, yeah. Okay, so we'll do that. So that's how we're going to do the two-letter combos. And then probability of the real words. Okay, here we use a lexicon. Okay, this is kind of like a dictionary with probabilities. All right, so caveat, the lexicon we're using kind of sucks. I mean, it's okay, but it's not that great. Okay, so the lexicon I have is not that great, and probably I have to find a better one. Okay, but okay, and so this one lists all of the words in English and has probabilities associated with them. So, you know, things like the word the, you know, I don't know, 0.02 or something, right? And then a is like 0.018 or something. I'm just, these are made up words, whereas probably the word house is something like 0.002, and then the word I don't know, what's an uncommon word? The ulna, which is, it's a bone in your wrist, arm, right? Okay, so that's probably going to be like 0.0000004 or something like that. Or maybe not that low, but okay, you know, much smaller. And then we also need for XJPQ, this is, you know, no entry. So words that have no entry. Now, we want to do is do not give this a 0 probability. Okay, because if you give it a 0 probability, then it means this mapping is impossible. We just have to give it a very unlikely probability, but a non-zero one. Okay, do not give a 0 probability, just give it a very small, very small probability. Okay, now the reason why I say our lexicon sucks is that it doesn't have plurals in it. So it's like that's a serious shortcoming. And the performance of our algorithm can probably be significantly improved by using word stems which will say, you know, words like runner, running, and runs all have the same word stem of run, okay? And houses and house all have the same, and housing all have the same word stem of house, okay? And that would solve our problem. I didn't feel like going through the effort of fixing it, okay? It works good enough, but, you know, our lexicon doesn't have plurals. So this is a, you know, a serious shortcoming, but can be fixed by using word stems. Okay, but I have not implemented it. Okay, so so this is what we've got. So we have a way to evaluate our two-letter combos and the real words. And again, we will use log probabilities to avoid issues with very small but non-zero values. Okay. All right. And then let's talk about the Metropolis algorithm then. Is everyone okay with this so far? Kind of following along our strategy? Okay, so we've got a way to evaluate our likelihood of the data. Okay, this is what we've got. We just need to find this, because this is a constant. The probability of our prior distribution is a constant. The marginal probability of the data itself is a constant. We're not going to worry about that. So we just have this. Okay. All right, so how does the Metropolis algorithm work? What do we need to do? We start off with an arbitrary mapping, and then what do? You start off with an arbitrary value, and then you propose. You propose a new value, right? So in this case, we're starting off with an arbitrary mapping, and we're going to propose a new mapping, okay? So we start with an arbitrary letter mapping, okay? And then we propose a new mapping, generally based on the current mapping, right? So we're going to propose a new mapping. So we propose a new value of theta based on our current value of theta. So all I'm going to do is I'm going to take our 26 letters in our current mapping. You know, it says A goes to K and B goes to, I don't know, whatever it was, G and stuff like that. And then we're going to propose a swap, okay? So let me just scroll back. So let's say this is my current mapping. Okay, copy that. And does this work? Oh, geez. Okay. This is going to take forever to scroll down. How do I move this down? Okay. All right. It would have been faster for me to just rewrite the alphabet here. Okay. Oh boy. Oh boy. All right. I got to figure out how to use this program effectively. I kind of like it. I don't know. Been using Sketchbook this entire time, but Sketchbook didn't work today, so something else. Okay. So we propose a new mapping. All right. So this is our current mapping. Right? And then the proposal is we just say, all right, here's a letter and here's a letter. Let's just say this, okay? And then we randomly select 2 letters, okay? Two letters to swap. Okay, so so our new mapping, A goes to K, B goes to Z, D goes to E, and what? No, sorry. C goes to E. Okay, the undo feature on this sucks though, okay. Okay, B goes to Z, C goes to E, and D goes to G, okay? Etc., 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 okay? And then so here we had, oh wait, no, this is the correct mapping. Okay, well anyway, you randomly select 2 letters to swap, and then you run the message through that, okay? So actually, I'm sorry, this is not a good example because this is actually the correct decoding, but sorry. Okay, actually. Not a good example because this is the correct. Okay, so anyway, you're supposed to start off with an arbitrary one, and then you swap 2 letters, okay? And then after you swap the 2 letters, then you run it through the evaluation, right? You calculate the likelihood. So with the new map, calculate probability of theta given D, which is proportional to this, right? So we run this through this, which is made up of probability of the 2 letter combos times, or in this case, probability of the real words, okay? All right, and then you calculate an acceptance ratio, which is going to be the min between 1 and your proposed map. This is wrong. Proposed mapping and your current. Okay. Which is equal to the min of, because it's proportional, we can just go straight to right. So we have this, okay, and we figure this out. That's your acceptance ratio, and then you either accept or reject the proposed mapping theta prime, okay? And then you let that run, and even though you start off with a terrible starting location, it should get you to a region of higher probability. Is that okay? All right, now here's one thing, okay. So an issue is we are using log probs log probabilities. So you know what we do is we draw U from uniform 0 to 1, and then we get log of U, and then our acceptance ratio which is probability of D given the proposed divided by D given the current becomes log of the proposed minus log of the current. Okay, and then we accept if log u is less than this. And reject otherwise. Does that kind of make sense? So we're not going to evaluate, there's 26 factorial possible mappings, okay? We don't have time to evaluate all those. So we just start off with an arbitrary one. We propose swapping two letters, okay? Maybe swapping two letters gives us more nonsense, but maybe that nonsense looks better than the other nonsense, okay? And if it does, we'll accept it. And if it doesn't, we're going to say, bah, we reject it. Okay. All right, so I have this all coded up. It's also posted on CCLE. And I hope this works. Every time I run code live for this class, sometimes it doesn't work. So, but I hope it works, and I'll talk through this. Okay, so here's my cipher code. So this is the first part, which is generating our 27 by 27 matrix of two-letter combinations to help us evaluate whether the two-letter combos are even good or bad in the first place. Okay. So first I'm going to read in the text of War and Peace. Okay. Oops. Session set working directly to source files. So this should do it. Okay. All right, and then so we can just kind of look at reference. Let's look at the first 10. All right. So. Okay, well, there's some funny characters in here. So it just says, the Project Gutenberg ebook of War and Peace by Leo Tolstoy. And so it just reads in this character thing, okay? And then what we're going to do is we're going to set up, I'm going to just run this in to upper, okay? And so now it's all caps. That's fine. And then we set up our 27 by 27 transition matrix. Okay, we can see that set up right here. And then we're going to give the transition matrix some letter names. Okay. So I can look at the transition matrix. All right, so it's 27 by 27. Right now everything has zeros, and it goes A through Z plus space, and A through Z and space, okay? And then we're going to say the last letter we saw was a space. Okay, and then this part just says go through go through this text and just say, okay, you see TH, put a tally at the intersection of T, the T row, and the column H, okay? Then the next thing that we see is HE, put a tally at the row H and the column E. And then it says E space, put a tally at the row E and the column space, okay? And it just does that, and there are 66,000 lines of War and Peace, okay? So it's going to just do that. It's going to say, if the current letter is this, do all of this. And it has a few things that's like, once you reach the end of the line, Leo Tolstoy, you hit the Y and you reach the end of the line, put a tally for Y followed by space, okay? And so on and so forth, okay? And just keep doing this. All right, so it's going to do that. It's going to take a little while to run, so I just let it go. I have it print out every 1,000 lines. Well, actually, I didn't write this code. This was from Andrew Landgraf. He wrote this, okay? And so, it's going through, it'll take you several hours to read through War and Peace. The computer reads it in about a minute or so. It still takes some time because we're having it do work for every single letter, right? If somebody said, you go through War and Peace and tally up the letters, it would take you a very long time and it'd be a miserable task. But we don't have to do that. We have the computers. They don't have feelings on the subject, not yet. And so it's going, and then it'll finish, okay? And let me just kind of explain the next line of code. Here I'm adding 1 to every single cell because there might be some cells that the combination never showed up, right? Like the letter Q followed by the letter J. That will probably never show up in the text, especially because this is a translation. And so, in the translations that you generally use regular English words and not made up ones. And so, we'll probably never see that. So, but we have problems when we have 0 probabilities, right? In a product, if you multiply something by 0, everything becomes 0. So we're going to add 1 to everything, and then we're going to sum up by the transition, by the total transit, by this thing. Okay. I should probably sum the transition matrix and 27 by 27. Okay, so we do this, and then we get our transition probability matrix. Okay, I have a few lines. Because it takes a little while to run through all 66,000 lines of code, you can save the resulting matrix, and then later on when you want to, if you want to work on the code again, instead of having to reload and read through War and Peace again on the computer, you can just save the matrix that it produced. Okay, so if we take a look at our transition probability matrix, if we take a look at this line, now we have probabilities for all 27 by 27 things. Okay, so now we have some numbers here, and so anyway, we can you can load that up. You can just save it and then load it later on, rather than having to start at the top. Okay, let me just show you the picture. Now they're advertising the books here when you load ggplot2. Okay, and so this is our 27 by 27 matrix. Okay, and we can see certain letters, certain combos are very common, right? T, there's the letter T followed by the letter H. This is very dark, meaning this is common. H followed by the letter E, also very common because of words like the. Okay, I followed by N is dark, that's common. And then if we look at other things that show up, N followed by G, N followed by D is common because of the words and stuff like that. Okay, Q followed by any letter is pretty much nothing. And then there's just a very faint square here for Q followed by U, okay? And then everything else is faint, or is nothing, right? So Q is never followed by any letter other than U, and even that is not all that common, right? And so you can see the columns that correspond to vowels, because those kind of follow many letters, right? Like A, E, I, O, and U is not that popular. Okay, and then other letters that, you can see the rows that correspond to vowels because they show up just darker in general. Okay, Z is pretty much light everywhere and stuff like that. Okay, and then here, this is space followed by A. This means lots of words begin with A, lots of words begin with T. Okay, and then these are letters followed by the space. So lots of words end with E, lots of words end with D, lots of words end with S, and lots of words end with T. Okay, so we have this 27 by 27 matrix that we can use to evaluate things. Okay, here's a function that will take a current mapping and coded text and spit out something else. Okay, so one potential map is just an arbitrary mapping of letters. Okay, so what this does is, so it just takes the letters A, and so A gets transformed into B, B gets transformed into I, C gets transformed into O, okay? And so I could run this through the function decode, okay? And we can take a look at X. And so hello, if we look at, A, B, C, D, E, F, G, oh wait, A, B, C, D, E, F, G, H, I, no, is it the other way? Okay, well maybe P, I'm not decoding the map, something. Okay, well the D map, oh, okay, and it's putting it the other way. Okay, so if I count to P, it gives me H, right? Okay, and then so if I look at the decoded, then A goes to this and stuff like that. And if I swap this around, then we could take in POJC and run it through the text, and we'll get back the word hello. Okay. And so we can run. This will be the log probability based on two-letter transitions. Okay. And so what this will do is it's going to kind of substring this, and it's going to look up HE, okay? So it's going to look at for 1 through the number of characters, and it's going to take, the current letter is what we have, and then the last letter is going to be, well, it starts off with the space, but in the next iteration, the last letter will be the current letter, and the current letter will be the next letter. And then it looks up in the matrix the row for the last letter and the column for the current letter, okay? And that will tell you, like, you have T followed by H, go to the row for T, go to the column for H, okay? And it's gonna find that value, throw it in the log function, and add that to the log probability, okay? And it does that, it adds that up, and it's gonna calculate the log probability of our word, all right? Is that okay? So this is going to find the log probability based on the two-letter transitions, as discussed. It looks up each combination, looks it up in the table, takes the log of that, and adds it. Okay, and it does that for each thing. Okay, over here I've got this lexical database. Okay, it's a big list, but let's just kind of look at it. Lexical.database. Let's look at the first one. Oops. Okay, so the word A has a probability of 0.016, and then the word AA has a probability of this. AAL has an even lower probability. I guess these are real words, okay? And so you can kind of see, probabilities of these things that are associated with kind of the words that appear in the English language, okay? And so here we're calculating the 1 gram probability. This just looks up the word and tells you the probability. So if I say 1 gram probability of the word A given our lexical database, it looks up that word, right? And we can say, what's the probability of the word house? And the word house has that. Let's see what the probability of ulna is, and the probability of ulna, which is a real word for the bone somewhere in your arm. It exists, but it's very low, right? And then meanwhile, if I look up the word, just type in some gibberish, okay? It returns back a non-zero but very small probability, right? So that's what it does. It looks it up. If it finds it, it'll give you that probability, and if not, it assigns a very small value. Now we can adjust this to see, how good or bad the words should be. Okay. All right, and then so the log probability of text takes the text, splits it up, finds the 1 gram probability, and returns the total log probability of the text. Okay, and so log probability of the text, I can say, a house is neat. And it says, okay, here's the probability there, where if I replace the word neat with gibberish, it tells you, okay, that's not likely, right? Okay, so it can tell us that this sequence is much more likely than this one, because this is what we have, right? And then meanwhile, if I have just all gibberish, gibberish, okay, that even has an even lower log probability, okay, which makes sense. Okay, so here our correct text will be enter Hamlet. This is Ham being Hamlet says, to be or not to be, that is the question, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against deceived troubles, and by opposing end. And so this is, from Shakespeare. Hamlet is debating what to do. Should he kill his uncle or not? He's not sure, right? And he can't decide, and that ends up being his downfall. So, all right, spoiler alert, sorry. Okay. Okay, so here we are going to just take a random sampling of letters, and this will be our current mapping, and we're going to scramble up the text, okay? So this is the true message that maybe the prisoners are sending to each other, and this is their coded text. This is the message that you've intercepted, okay? So this is what we have. And we go, oh man, what are the prisoners saying to each other? Okay, they're just sharing Shakespeare, but we don't know that. We want to know, are they talking about, attacking the guards and whatever, or, whatever. Okay, so this is what we've intercepted, and we want to figure out what was the true message, okay? So we have no idea what a good mapping is, so we're just going to randomly start off with a terrible mapping, okay? We're going to say, okay, this is how we're going to map the letters, okay? Now, if we run our current text, okay, this is our coded text, okay, if we run that through it, okay, this is what we get, okay? Our current decode looks like this, okay? Now we have afpak neo map neo pid tad, okay? And we're trying to see, okay, so we're going to start off with this as a decode, and we're going to say, well, that doesn't seem quite right. Can we find something better, okay? But we're going to find the log probability based on our two-letter transitions, and we get this number. And then we say, okay, well, are any of these like real words? And then we do that, and we get a very negative number, okay? And then, because these are kind of like two strategies for evaluating the probability, we can weight one versus the other, okay? And so here, I'm taking the two-letter probability, and then I'm weighting this one to be less, okay? Okay, and this is something that you can kind of tweak, and we'll see what happens. Okay, and so when I combine these after weighting them, this is my score here. Okay, and we're going to say, all right, we're just going to we're going to say this is my current mapping. Okay, and then what I'm going to do, I'm going to run this 500 iterations. But what I'm going to do is I'm going to propose a new mapping. Okay, so the proposal is we're going to say, let's swap the letters 11 and 9, okay? So our current mapping is this, okay? And what we're going to do is we're going to swap the letters for 11 and 9, okay? And then so my proposed mapping now, okay, is exactly the same as our current mapping, except the letters 11 and 9 have been swapped. Okay? And then we run that. So our current decode is this. After swapping those letters, my proposed decode will be this. Okay? Pretty much exactly the same, except where we used to have the 11th and 9th letters. Let's see. What has changed? Okay, so the K has become, so the 11th letter, I guess, is K, and the 9th letter is I. And so where there used to be a K, it's now an I, and where there used to be an I, it's now a K, okay? And we say, okay, well, which one seems more likely, okay? And so we run the proposed text through it, and we get our proposed combined likelihood, okay? So if we compare our current combined log likelihood, it's this. The proposal is kind of worse, okay? It's negative 1710 versus negative 1765, okay? So this one is technically worse, okay? Our proposed mapping is less likely according to our evaluation methods, okay? And then so what we do is we are going to, well, I guess we take, why did I do this? For some reason, instead of taking the log of our unif, I'm raising this to the exponent. And why did I multiply this by 0.5? This is weird. All right. I'm going to do a change here. Okay, so I'm going to, if log of the random uniform is less than the difference between the proposed and the current log likelihood, this makes sense to me, we will swap them, okay? We're going to do, make the proposed mapping our current mapping, and then our proposed decoder to our current decode, okay? And we just replace with everything, okay? And if it's even better than what we ever saw, we'll do that. Okay. You might have to I'll have to re-upload the cipher code there. Okay, so we'll do that, and then we just run that. We'll do 500 iterations of that, okay? So here is our current decode, and then does this ever print? Proposed combined. Oh, okay, yeah, we printed out. Cat it to the screen. Okay, so let's try this out. Let's try this out. So it's going to start off here. I hope this works. I just made a change to my code here, so I hope this works. Okay, so it starts off, and everything, like, it looks not like good. But, you know, I mean, we can see how it's kind of ending up here, because at least these look like kind of like words. They're not real words, and so it's just proposing swaps. Here, one thing that we're missing, and the reason why it's kind of taking a long time to run, is that when it proposes a bad swap and it rejects it, we don't get to see those. And here it's only kind of printing out when it actually changes, okay? Normally, when you're sampling, if you reject something, you keep the current one and you use that again, okay? So it's doing that, but here we're not We're not swapping these, okay? Now we're starting to get things. It's saying like, okay, these might not actually be true solutions here, but we're getting letters that look reasonable, okay? We're getting words like it and are and in are find. Okay, and then and so here we have the word be, and it should be to be or not to be, but it says as be, as be. So it's gotten the mapping for be here correct, and I I'm like nervous that this is not going to work at the end of the day, but we can see that it's searching, and these are they are not correct. But it's we're hoping it's moving in the correct direction here. And I just made a change to my code, so I'm wondering, I don't know if that messed anything up, but we'll let it run. It seems to be stuck on something, huh? Let me check. Maybe I... Let me check this code and see if it's any better. Okay, still have this. All right, maybe this is what I was supposed to use. I don't know. That seems weird. All right, how are we doing here? Oh, it's getting better. Okay, it says ensur, not enter Hamlet. It says ensur and halfwes, half so be, ol nas so be. So instead of to be or not to be, it's got, oh, look at that. It's got it. To be, ol not to be. That is the Russian. Oh, we're getting there. Okay. And it's just searching. All it's doing is it's just swapping two letters at a time, and it says, is this better? Is this better? And the way we're evaluating is evaluating the that is the question, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous. That is the question, it says, okay? Hey, we got there. Look at that. Huh? Enter Hamlet, to be or not to be, that is the question with a C, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to, and it should say take arms. Oh, look at that. Take arms against a sea of troubles and by opposing end. And it will probably struggle to find better mappings at this point, okay? So, so we had to endure a lot of kind of bad proposals and things like that. Hey, look at that. It got there. It's not sure, right? It doesn't understand, it doesn't know the difference. So here it's, proposing taste versus take, small things. It's swapping letters, probably letters that haven't, don't even appear in the text here. Okay. All right. Well, I'm happy. It worked out. So we'll go ahead and stop there. I was nervous that I did something wrong in my code, but I hope this was at least an interesting and enjoyable application of the Metropolis algorithm, showing in situations where we never calculated the normalizing constant, because the true probability distribution over the space of all 26 factorial possible mappings, that's something very complicated and something we'll probably not have the power to calculate straight up. But by using the Metropolis algorithm, we're able to draw a sample from this abstract space that exists out there and get proposed mappings that correspond to high probabilities. Okay? All right, we'll wrap up here for today, and then we'll see you guys on Thursday. We'll talk more about Markov chain stuff.